In the last module, you learned about variable frequency drives and how they control motors. We briefly touched on how motor speed sensors help the VFD maintain the correct speed. This module takes a deeper dive into these sensors, which are called encoders. They belong to both the drives and the I/O pillars of automation. Encoders directly affect drive operation, but they're sensors too. We'll explore what they do and how they make sophisticated industrial automation possible. An encoder provides feedback so the VFD knows how fast the motor is turning. Without feedback, the VFD can only estimate the motor's speed. With feedback, the VFD can continuously tweak the speed to maintain the set point, the speed that you've specified. This is called closed loop control, and it's crucial to precision applications. This diagram shows why we call it closed loop. The VFD operates the motor by controlling its power delivered over the motor power cable. The encoder reports the motor's speed back to the VFD over the encoder cable. The VFD uses this information to adjust the motor's speed, and the process goes on and on in an endless loop. When you give the VFD a new set point, it immediately detects the difference between it and the current speed as reported by the encoder. It starts accelerating the motor toward the set point. Notice how the motor overshoots. The encoder reports this to the VFD, which slows the motor. The motor then undershoots the set point, so the VFD increases the speed slightly. Eventually, the motor settles at a speed very close to the set point, while the VFD continues to monitor the encoder and make slight corrections. As you can see, the encoder plays a vital role in precision control. Encoders come in many styles and performance levels. We won't cover every type, but we'll look at the most common ones. A motor encoder attaches to the motor's B end and connects directly to the motor shaft. This lets it accurately monitor the motor's motion. Motor encoders come in two styles. An external encoder is a separate device that bolts onto the motor. You can have one installed at the factory or add one onto an existing motor. Internal encoders are part of the motor's design. This example is part of the fan, so it's very compact. Just a quick warning. In the next few minutes, you'll see several animations that include flashing lights and graphics. If you react to these, please look away. Incremental encoders are the most common motor encoders for speed monitoring. They're relatively inexpensive. The encoder outputs electrical pulses called increments as it turns. The faster the motor spins, the faster the encoder outputs those pulses. The VFD times the increments and calculates the motor's speed from them. The more increments the encoder outputs per revolution, the higher its resolution. The higher the encoder's resolution, the more accurately the VFD can control the speed. As you can imagine, however, the higher the resolution, the more expensive the encoder will be. For applications requiring only moderate accuracy, a low or medium resolution encoder may be perfectly acceptable. Incremental encoders use one of several technologies to generate their pulses. Many incremental encoders are optical, relying on a transparent disc marked with black lines and rotating between a light source and light sensors. This encoder disc has three concentric tracks around its edge. The first is the index track, or Z-track. It has just one mark, which indicates when the encoder is at its zero position. The second and third tracks are the A and B tracks. They're identical except that they're offset from each other by half the width of a black mark. In a few moments, you'll see why they're set up this way. A light source shines through the disc. As it turns, the black lines interrupt the light, making it appear to blink. The faster the disc turns, the faster the light blinks. Three sensors on the opposite side detect the flashes and generate the electrical pulses. Notice that there's just one Z pulse per revolution, but many A and B pulses. Also notice that the A and B pulses are offset, just as the marks on their tracks are offset. What's the purpose for this? Because they're offset, the A and B tracks enable the VFD to determine the rotation direction. Pretty clever. Incremental encoders are excellent for speed monitoring, but absolute encoders are a better choice if the motor performs positioning. Positioning applications can be much more demanding than those that just run the motor at different speeds. This palletizer contains multiple motors that must move a specific number of turns to transfer boxes from the conveyor onto the pallet. Unlike an incremental encoder, which outputs pulses as it turns, an absolute encoder outputs a unique number for each rotational position. The VFD uses these numbers to move the application's specific distances. For example, this absolute encoder outputs numbers from 0 to 32,767 as it turns through one rotation. This means that it's possible to detect rotations as small as 11 thousandths of 1 degree. As a side note, I'll mention that you can do positioning with an incremental encoder, but it isn't as easy because the VFD loses the current position if you turn it off. An absolute encoder always remembers its current position even when switched off. For this reason, absolute encoders are more common in positioning applications. Unfortunately, they're much more expensive, and many are rather delicate. Like incremental encoders, many absolute encoders are optical as well, but their disks are a lot more complex. This encoder disk reports just 8 positions per rotation. Notice that it has 3 concentric tracks. These generate 3-bit binary numbers as the disk rotates. Again, a light sensor goes on one side, while a light source goes on the other. In this case, there are 3 sensors since there are 3 tracks. As the disk turns, the encoder outputs a modified binary code that translates to the position numbers. The VFD uses these to know the motor shaft's rotational position. Notice that the positions repeat after the disk has completed one rotation. This means that the encoder is single turn. If the VFD needs to rotate the motor through multiple turns, it will have to keep its own count of complete rotations. For this reason, single-turn encoders are best for positioning applications that move relatively small distances. For applications that must move longer distances, there is a better choice. A multi-turn encoder has an electronic counter that keeps track of complete rotations. Notice that as the encoder disk turns, the positions repeat after each rotation, but the counter keeps track of the individual rotations. The encoder combines the rotation count and position value into a single number. What it actually outputs is a long string of unique numbers. Some encoders will generate millions of unique positions before they return to 0. Many absolute encoders include incremental tracks, so the VFD can use the encoder for both speed control and positioning. This encoder disk has 3 incremental tracks on the outside and 3 absolute tracks on the inside. Remember that an encoder's performance depends on its resolution. Higher is usually better, but costs more. Incremental encoders are specified by increments per revolution. This ES7S incremental encoder outputs 1024 increments per revolution, which supports precision speed control. Single-turn absolute encoders are specified by their number of unique positions. This is expressed as a binary number. This EK8W encoder has a resolution of 16 bits, which means that it outputs 65,536 unique positions in a single rotation. It also includes incremental tracks and has an incremental resolution of 2048 increments per revolution. Multi-turn absolute encoders are specified by two numbers: their number of unique positions and the number of rotations they can count. This is expressed as two binary numbers. This AK0H has 12 bits of resolution and 12 bits of rotation counting. In other words, it outputs 4,096 unique positions in a single rotation and can keep track of 4,096 individual rotations. To figure out the total number of unique numbers that it will output, take 2 and raise it to the sum of the two numbers. 2 raised to the power of 12 plus 12, which equals 24, gives 16,777,216 total positions. Notice that this encoder also has incremental tracks, but they give relatively low resolution speed control since the encoder outputs just 128 increments per revolution. Sometimes the motor encoder alone isn't sufficient to manage the application, so industrial automation systems often include additional encoders that aren't attached to the motor. Here's an example that explains why this can be necessary. This travel drive is belt-driven, so a motor encoder isn't reliable enough for positioning. Why not? Notice that a belt running over two pulleys moves the carriage. If the belt slips during positioning, the motor encoder won't detect it and the position it reports won't be accurate. To fix the problem, we add a second encoder. A laser encoder mounted on the travel carriage will accurately report its position to the VFD. Since the encoder is on the carriage, belt slip won't affect its accuracy. Laser encoders continually shoot a laser beam at a target and time the reflection. Using this information, they compute their position relative to the target. Some models can detect positions down to a fraction of a millimeter. In this kind of application, the motor will also have an encoder for speed control, while the laser encoder provides the positioning data. The VFD will process both encoder data streams to position the carriage. Here's another example. This overhead conveyor needs to position the tires at specific locations. To do this, we use an encoder that scans the track itself. A barcode linear encoder reads a barcode on the track and reports the position to the VFD. This encoder type is good for moving products to specific locations rather than specific distances. Again, the motor will also have an encoder so the VFD can control the speed. Vertical applications frequently use yet another encoder technology. For hoists, a draw wire linear encoder reports the vertical position to the VFD. With this gantry hoist, the encoder mounts on the floor and a wire links it to the section that moves up and down. As the hoist ascends and descends, the encoder reports the vertical position to the VFD. Perhaps you're wondering how it works. Let's see. Taking the cover off reveals a spool of wire inside. It's spring-loaded, just like a tape measure. As the hoist moves up and down, it pulls the wire in and out, causing the spool to rotate. A rotary absolute encoder mounted on the cover and attached to the spool generates the positions. Pretty simple and rather clever. This is a good time to mention that while many encoders are optical, other technologies, such as magnetic sensing, are common too. This EI8R internal incremental encoder uses a magnetic ring embedded in the motor fan to generate increments. As the fan turns, a sensor board mounted nearby measures the changing magnetic field and turns this information into pulses. Encoders are extremely useful, but many are both fragile and expensive. A resolver is an economical and durable alternative to an encoder. They are very common in servo motors, such as this CMP servo motor, which contains an RH1M resolver. So, what's the difference between an encoder and a resolver? Many encoders are digital, outputting pulses or numbers. Resolvers are analog, outputting a changing voltage. The VFD digitizes the voltage and applies some math to convert it to a numeric position. Resolvers are functionally equivalent to a medium resolution, single turn absolute encoder. Be aware, however, that not all VFDs support resolvers, although many of SEW Eurodrives do. Let's watch a resolver in action to see how it works. Resolvers are like rotating electrical transformers. The outer component is the stator. It contains 3 coils. The inner component, which spins, is the rotor. It contains 2 coils. We energize the resolver by applying a 7 kHz AC signal to one stator coil. This generates a pulsating magnetic field that induces a voltage in one rotor coil. That voltage generates a magnetic field in the second rotor coil. As the rotor spins, it induces a voltage in the other 2 stator coils. These coils output 2 signals that rise and fall in a sinusoidal pattern. We label these signals S and C, which stands for sine and cosine. The VFD converts these signals to numbers and does some trigonometry with them. The result is the rotor's angle with respect to the stator. As the rotor spins, the signals change, which generates a series of positions. We'll wrap up this module by examining how different encoders connect to the VFD. Every encoder communicates with the VFD using a set of electrical specifications called an interface. An encoder cable links the encoder's interface to a matching interface on the VFD. Obviously, the VFD must support the encoder's interface standard to communicate with it. SEW Eurodrive's Generation C VFDs, such as this MoviDrive technology, support many industry standards. The first 3 work with incremental encoders. The next 3 work with absolute encoders or resolvers. And the last one, MoviLink DDI, supports encoders of both types. As a bonus, some encoders include an electronic nameplate. This electronically contains the same information as the motor's physical nameplate. The nameplate communicates with the VFD over the encoder interface, speeding up motor commissioning. Most encoder interfaces use a dedicated cable, but some share a hybrid cable with the motor itself. Hybrid cables contain multiple wires that provide power, control the brake, and carry data streams. These data streams can communicate encoder information, the motor's temperature, and electronic nameplate information. Hybrid cables offer the customer the convenience of a single cable solution. They're becoming increasingly popular, and several major industrial automation manufacturers, including SEW Eurodrive, support them. Let's survey some of the most popular interfaces. The sine-cosine interface is common on incremental encoders. It uses a dedicated encoder cable to send 2 analog signals to the VFD. By combining these signals, the VFD quadruples the encoder's actual resolution. For example, if the encoder generates 1024 increments per revolution, the VFD will detect 4096 increments per revolution. This is the reason for the sine-cosine interface's popularity. The TTL or RS422 interface and the HTL interface are found on some incremental encoders. They send a pulse signal over a dedicated encoder cable. They're nearly identical except for their signaling voltages. These interfaces are commonly used with lower-end VFDs that don't support the more sophisticated interface standards. The Hyperface and SEW RS485 interfaces are found on absolute encoders. They're nearly identical functionally. These interfaces are actually two separate interfaces in one and communicate over a dedicated encoder cable. The first interface sends a digital stream of position values to the VFD. The second interface is a sine-cosine interface and communicates the encoder's incremental data to the VFD for speed control. Encoders with these interfaces often contain electronic nameplates. The MoviLink DDI interface communicates incremental and/or absolute data over a hybrid motor cable. This sophisticated single-cable solution works in tandem with SEW Eurodrive's MoviLink DDI-equipped motors to send multiple digital data streams to the VFD. These can carry encoder information, electronic nameplate data, and motor sensor data. Finally, the resolver interface sends absolute position data over a dedicated encoder cable as a pair of analog signals. The VFD processes these into numerical positions. With that, we wrap up encoders. In the next module, we'll explore the sensors that supply data to industrial automation systems, helping them to make decisions and preventing problems. You'll learn how VFDs and other control devices connect to these sensors and respond to the information they supply. And finally, we'll look at various output devices that help control industrial automation equipment and alert human operators to what's going on. See you next time.